Hello, everyone. I hope you are all having a great day so far. So, this will be our lecture on section 1.1 exponents, orders of operation, and inequalities. So, let's get started. Our objectives today are going to be to, number one, use exponents. Number two, use the rules for order of operations. Number three, use more than one grouping symbol. Number four, know the meanings of not equal to, less than, greater than, less than or equal to, and greater than or equal to. Number five, translate word statements to symbols. And number six, write statements that change the direction of inequality symbols. So beginning with objective one, use exponents. We can say that since we can write numbers as product of prime numbers, we can write any number as a product of prime numbers to say, sometimes we get something that looks like this. So we have a number here, we have 16 is equal to 2 times 2 times 2 times 2. This would be the prime factorization of 16, and the prime factorization of 16 is 2 times 2 times 2 times 2, so 2 multiplied by itself 4 separate times. We see here that the number 2 appears 4 times, and we can express the repeated factors as exponents. So we see here when we have our 2 times 2 times 2 times 2, we have this highlighted as 4 factors of 2, and this is equal to 2 to the 4th power. So however many times 2 itself is being multiplied is going to be our number in our exponent. So since we multiplied 2 4 times, we have 4 in our exponent, and 2 will become our base. So we see here our base highlighted in green is going to be this number 2. So whatever the actual number is that you're multiplying multiple times, and the exponent is how many times you multiplied that number by. So in the exponential expression 2 to the 4th power, the number 4 is the exponent and the number 2 is the base, which we already went over. The exponent tells us how many times the base is used as a factor. So as an example again, let's get the pen out here. So as an example, if we have 3 times 3, 3 is going to become our base because that's the actual number that we're multiplying, and we see that we multiply it twice. So if we multiply it twice, 3 times 3 will become 3 to the 2nd power, or 3 with a superscript of 2. Then we have 4 times 4 times 4. So 4 is our base because that's our actual number. And we see 4 is multiplied 3 times. So 3 is our exponent. Then we see we have 1 times 1 times 1 times 1 times 1 times 1 is equal to 1, which is our base, which is the actual number we're multiplying out, 6 times. So our exponent is going to be 6. So all that we're doing is we're taking this number that's being multiplied by itself multiple times, and we're just finding another way to express it. So instead of having this long chain of the same number being multiplied out, we can just simply say that number 2, or have the exponent of however many times you multiplied that factor out. So when we see the number 2 with an exponent of 4, we're going to read this as 2 to the 4th power, or just 2 to the 4th. You can also hear it said as 2 to the power of 4, or anything along those lines. So this is just how we would normally say it when we see the base 2 with an exponent of 4. We would say 2 to the 4th power, or 2 to the 4th, or 2 to the power of 4. All of these mean the same thing, just different ways we express out our exponential expressions. So a number raised to the 1st power is simply that number. So any number, so if we had 1,000,000 raised to the power of 1, that's just 1,000,000. So any number that we raise to the power of 1 is just going to be itself. So for our example here, we have 1,000 to the 1st power, and that will be equal to itself, 1,000. Then we have 1.23 to the power of 1. So our answer will be 1.23. Similarly, 1 raised to the power of any number is always going to be 1. So as before, when we saw our 1 to the power of 6, that answer is going to just be 1. All right, as a note of caution from your book, we see that squaring or raising a number to the second power is not the same as doubling the number. In example 1a from your book, we were given 5 squared, or 5 to the power of 2, or 5 to the second power, many different ways we can say this, means 5 times 5 and not 5 times 2. So 5 squared is equal to 25 and not 10. Similarly, cubing or raising a number to the third power does not mean tripling the number. In example 1b out of your book, we see that 6 cubed, or 6 to the third power, cubed is just another way of saying to the third power, the same way that squared is the same thing as saying to the second power. That 6 cubed is equal to 216, not 18. So when we see these exponents, it means that we are multiplying whatever our base is that many times, not our base times our exponent. So very important thing to remember when working with exponents. All right, on to objective 2. We want to use the rules for order of operations. When an expression involves more than one operation, we often use grouping symbols such as parentheses, brackets, or braces. So our parentheses are what our normal curved parentheses would look like. So we see curved parentheses, brackets are our squares, and our braces are these ones that look curly. So we have our parentheses, brackets, and braces. The most common one we see is going to be parentheses. And we use these to indicate which operation should be done first. So for an example, if we want to consider 5 plus 2 times 3 is equal to what? Now, if we have 5 plus 2 times 3, we can use our parentheses to kind of separate things out. So 5 plus 2 times 3 at this point, since we don't really know our order of operations quite yet, we can't really decide how we're going to solve this value. So what we can do is we can add parentheses. And let's say we add parentheses around 5 plus 2. So now we have 5 plus 2 times 3. And what we're going to do is that we're going to calculate whatever's in our parentheses first. So 5 plus 2 in this case is going to be 7. So we say that this is equal to 7 times 3, which is equal to 21. Now, let's put our parentheses around 2 times 3. So if we say 5 plus 2 times 3, we want to do whatever's on our parentheses first. So 2 times 3 is going to be 6. And we end up with 5 plus 6. And that answer is going to give us 11. Now, 11 and 21 are not equal to each other. So this just goes to show that wherever you put your parentheses, it's going to be very important, because when we get to order of operations, the first thing we do is whatever is in our parentheses. So when simplifying an expression involving more than one operation, we need to use order of operations. So our order of operations is telling us that if grouping symbols are present, so these are parentheses, brackets, braces, work within them innermost first and above and below fraction bars separately in the following order. So step 1, we want to apply all exponents. Step 2, we want to do any multiplications or divisions in order from left to right. Step 3, do any additions or subtractions in order from left to right. If no grouping symbols are present, we just begin with step 1. So whenever we have grouping symbols, whatever it is, we're going to follow our order of operations inside those parentheses. in order to solve what's inside our parentheses. And once we've done that, or inside our grouping symbols, and once we've done that, then we can go through the steps again to solve for the entire expression. So you work inside out, and you also work from left to right. Something that you may all know, or maybe not, which is perfectly okay. The order of operations can also be referred to as PEMDAS. So this is just another way to kind of remember things when you're working through them. So if you can remember PEMDAS, it's the order of operations in steps. So step 1 would be parentheses, brackets, braces. You want to do anything that's in parentheses, brackets, or braces. Step 2, you want to apply any exponents. Step 3, which is considered multiplication and division. So let's actually write these out. So we hear this is step 1, step 2, and then we have step 3 and step 4. So step 3 would be our multiplication and division. Not necessarily in this order. You want to move from left to right, or you want to work from left to right. Same goes with addition and subtraction. You don't have to add before subtracting. You just want to move left to right. This is technically in 4 steps, since our grouping symbols are not entirely considered a step. So I guess we could call this step A, and then go from there. So that follows along with our order of operations a little bit better. But if PEMDAS is easier to remember for order of operations, feel free to use this as well. Just remember to really cement in those details of really what comes first and what directions you should be moving in. All right, so let's work with some examples here. For our first example, 24 minus 12 divided by 3. We don't have any grouping symbols in this case, so we're just going to go from step 1. Step 1 would be to apply all exponents. Well, we don't have any exponents, so we don't really have to worry about that. Step 2, do any multiplications or divisions in order from left to right. Our first step here is 24 minus 12, but we're on step 2 with multiplication and division, so we're going to pass it. Our next numbers here are 12 divided by 3. Well, that's division, and that's in step 2. So we need to divide 12 by 3 first. So we're going to divide 12 by 3. So we're going to end up with 24 minus 4. And we can identify this as step 2. Now what we're left is 24 minus 4. We have finished our step 2. There's no more multiplications or divisions, so now we're going to move on to step 3. And step 3 is do any additions or subtractions in order from left to right. So we have 24 minus 4. No addition, but we do have subtraction. And we move from left to right. So we are subtracting 4 from 24. And this is going to give us 20. And we see here that this was step 3. All right, so one more example here to really solidify it a little bit more. So we have 3 times 2 plus 4. So whenever we have a number outside of parentheses, this is going to indicate to us multiplication. So let's make note of this now. So we can say indicates multiplication. All right. Then our first step here in our order of operations is working with our grouping symbols. So we say if grouping symbols are present, work within them innermost first and above and below fraction bar separately in the following order. So because we have a grouping symbol, we're going to follow step 1, 2, and 3 until we have solved whatever is inside of our parentheses. And then we will go again, step 1, 2, 3, in order to solve for our expression. All right, so we have 3 times 2 plus 4. 2 plus 4 with our grouping symbols, we want to solve first. So inside of parentheses, step 1, we want to apply all exponents. We don't have any exponents, so we'll go on to step 2. Step 2, do any multiplications or divisions in order from left to right. Well, inside of our parentheses, we only have a 2 plus 4, so we're going to skip step 2. Then in step 3, do any additions or subtractions in order from left to right. 2 plus 4, that's addition. So, moving from left to right, this is going to give us 3 times 6. So we can rewrite this again as just 3 times 6. And now, since we have an expression without any grouping symbols, we want to go through our steps again in order to solve. So step 1, we want to apply all exponents, no exponents. Step 2, do any multiplications or divisions in order from left to right. And we see we do have multiplication, and this will give us 18. Since 18 is our final answer, there's no need to go on to step 3. But let us factor these in. So 2 plus 4 was a step 3 with grouping symbols. 3 times 6 ended up being a step 2, and we're going to say without grouping symbols. And that gave us our answer of 18. All right, on to objective 3. Objective 3, we want to use more than one grouping symbol. So now we're using multiple grouping symbols. So when we're using grouping symbols, if an expression needs more than one set, we often use different types of grouping symbols. So instead of having 2 with parentheses around 8 plus 3 with parentheses around 6 plus 5, we're going to use different types of grouping symbols. So instead of using multiple parentheses, we're going to use parentheses and brackets. So instead, we're going to have 2 with brackets of 8 plus 3 times parentheses 6 plus 5. So remember, when you're solving these expressions, you always want to work from the inside out. So when we have these multiple sets of parentheses, whatever set is the innermost, you start there and you start working outwards. So let's work through an example. So we have 2 times 8 plus 3 times 6 plus 5. So the first thing we want to do is solve 6 plus 5. This is first. I'm just going to write the number 1 instead. So this is first. So we're going to write everything else the same. We're just going to solve whatever is in our innermost parentheses. So we have 2 times 8 plus 3 times 6 plus 5, which is 11. We can also write this as 3 times 11. Now we have 2 times bracket of 8 plus 3 times 11. So we have another set of grouping symbols here. So, like our order of operations say, whenever we have grouping symbols, we always want to deal with those first. So now our second step here is going to be solving what's inside of our brackets. And we'll need to use our order of operations here as well. And what we see here, if we only consider our brackets, we have 8 plus 3 times 11. There are no exponents, but we do have multiplication. So we do have to use our step 2 before we go on to our step 3. So 3 times 11 is step 2. Just like before when 6 plus 5 was a step 3. So we still have 2 multiplied outside of our brackets, but now we're going to have 8 plus whatever 3 times 11 is, which is 33. And now we have 2 times something in brackets, with something being 8 plus 33. So now this is our third step we want to take. And what we see inside of our parentheses is 8 plus 33. Since we already did our step 2 with multiplication and division, we move on to step 3, which includes addition and subtraction. So this is now step 3. So solving for step 3, we're going to end up with 2 times whatever's in our brackets, which was 8 plus 33, which is going to end up being 51. I think I did that wrong. 41. See, mental math is hard. All right, so we have 2 times 41 here. So we know that having a 2 multiplied by something in a bracket, we know this just stands for multiplication. So we're going to say it's 2 times 41. And this will be our last step, or our fourth item to solve. And in our order of operation coincides with step 2, multiplication. And this gives us our answer of 82. So using our order of operations, we were able to solve this longer expression with multiple grouping symbols, and we were able to come to our answer using the different steps of our order of operations and really identifying what parts of our expression we were going to solve first. All right, and just a note from your book, we have an expression from example 3b, which ends up being 4 times, parentheses, 5 plus 3, plus 3, divided by 3 times 2, minus 1. And we're saying that this can be written as a quotient. So whenever we have fractions like these, we want to write them out as quotients because that helps us follow along with our order of operations. So we can always rewrite this, and we're going to give the numerator and the denominator brackets since we have already written parentheses at one time. And we're going to say that in brackets, 4 times, in parentheses, 5 plus 3, divided by 3 times 2 minus 1, all in brackets. So we say that the fraction bar groups the numerator and the denominator separately. And remember, our numerator will always be written first, and then our division symbol, and then our denominator. So whenever you have fractions like this, you can always rewrite them as quotients in order to follow along with your order of operations. All right, so objective 4, know the meanings of not equal to, less than, greater than, less than or equal to, and greater than or equal to. So these are all symbols that obviously stand for phrases at this point, since I've said them already. But so far we know the equality symbol, which is 2 parallel lines going horizontally. But we do not know the inequality symbols, which are the ones we just went over. So we have not equal to, less than, greater than, less than or equal to, and greater than or equal to. So these are used to express an inequality, a statement used to show two expressions may not be equal. So starting with our first symbol here, we have the equality symbol with the slash through it, written again, means not equal to. And this would just be represented in order to show that any number was not equal to another number. So for example, 7 is not equal to 8, just like 2 is not equal to 10, and 1,000 is not equal to 1,000,000. If two numbers are not equal, then this means that one of them must be less than the other. So if we're reading from left to right, the less than sign, or this sign, means is less than. So for example, 7 is less than 8. And we want to read these from left to right. So whenever we have our less than sign, we have our number that is lesser on the left and the number that is greater on the right. If two numbers are not equal, one must also be greater. So in addition to having one number that is less than the other, we also have the number that is greater than the other. So once again, reading from left to right, the greater than symbol, or this symbol, means is greater than. So for example, 8 is greater than 7. So whenever using the greater than sign, your number that is greater or more, in essence, is going to be on the left-hand side, and the number that is smaller is going to be on the right-hand side. So if either less than or equal is true, then the inequality less than or equal to is also true. So it just needs one of those two things to be correct. So for example, 5 is less than or equal to 9. 5 is obviously less than 9, but since 5 is less than 9, we can always say that 5 is less than or equal to 9, since less than is true, and you only need less than or equal to satisfy that inequality. So in our example, we can say that 5 is less than or equal to 9. 9 is also less than or equal to 9, because they're equal. And 5 is also less than or equal to 5, since 5 is equal to 5. Same goes for greater than. So if greater than or equal to is true, then the inequality greater than or equal to is true. So we're basically combining these two. We're combining an inequality with an equality. So we're saying if this one inequality is true, or if an equality is true, we're combining these to create one symbol, and if either of them are true, the statement must be true as well. So for an example, 4 is greater than or equal to 2. 4 is obviously greater than 2, but since it satisfies one of its conditions, we can also say that 4 is greater than or equal to 2. We can also say that 4 is greater than or equal to 4, since 4 is equal to 4, and 2 is also greater than or equal to 2, since 2 is equal to 2. So to help remember less than, greater than, less than or equal to, and greater than or equal to, the symbol always points to the lesser number. So when trying to write them out, whichever inequality you're going to use, whichever way you write it, the point has to be going towards the smaller number. So when we see here, 8 is less than or equal to 15, we see our symbol is pointing or has its sharp point at the end with the smaller number. Then we also say 20 is less than 5. Our symbol is pointing to 5. 100 is less than 101. Our symbol is pointing to 100. And we have 1.1 is greater than or equal to 1.01. And our symbol is pointing towards 1.01. All right, objective 5. We want to translate word statements into symbols. So we can express the symbols we just learned as statements and translate them from word problems. So being able to translate them becomes really helpful in working with word problems that are inevitably going to come up on your homework and potentially even midterms. So we want to be able to translate these statements and write them as mathematical expressions. So in our example, we have 9 plus 2 is equal to 11, all written out in words, but we want to rewrite them now as expressions. So we start with 9, so 9 plus, so we have addition, 2 is equal to 11. So we have equal to, our one equality is equal to 11. Fairly straightforward. It's a normal equality that we would always use anyway. Next one is 30 is less than or equal to 50. So we begin with 30, and we're saying that 30 is less than or equal to 50. Well, 30 is less than 50, and our symbol for less than looks like that. We're also saying that it is less than or equal to, so we have to include our line underneath. Then our last statement is 50. So we have 30 is less than or equal to 50. To check and see if that's right, we can see our symbol is pointing towards the smaller number. So we can say that that is correct. Our last example here is 3 is not equal to 5. So we begin with 3, and we're saying it's not equal. So remember, our not equal sign is just an equal sign with a slash through it. So we say 3 is not equal to 5. And we know that 3 is not equal to 5, so this statement is true. All right, now our last objective here, we want to write statements that change the direction of inequality symbols. So a statement with the less than symbol can be changed to one with a greater than symbol, and vice versa, and also with less than or equal to and greater than or equal to, by changing just the phrasing. We do this by reversing both, so we have to do both of these things. We do this by reversing both the order of the numbers and the direction of the symbol. So in an example here, we have that 7 is less than 10. We want to be able to reverse these, or reverse our statement to say that 10 is greater than 7. So when we reverse this, 7 is less than 10. We want to reverse the order of the number. So we're going to flip the 7 and the 10. So now we have 10 and 7. And something goes in the middle. We also want to flip the direction of the symbol. So our symbol, which was pointing towards the 7, still wants to point to the 7. But now our 7 has moved, so our symbol has to move as well. So our symbol points to the 7, and we see we have flipped our symbol. These expressions are the same. We are stating that one number is less than another number, and also that that number is greater than the first. So these are equivalent expressions, so they are the same. We have just rewritten it. So what we did here was that we reversed the symbol and we reversed the order of the numbers. So all right, now going through all of our different inequalities, here we have a summary. So this table is very helpful, it can be found in your book, and it just kind of goes over the symbol, meaning, and then common examples. So we have our symbols too, which is equal to, our first example being 0.5 is equal to 1/2. And that means 0.5 is equal to 1/2. Obviously, reading it, you get a little bit more out of it than me reading it to you because it just sounds like I'm saying it twice. But as you can see, using the symbols versus using the expressions, we can kind of look through the examples and better understand the meaning. So if at any point you would like to have a little copy of all the summaries of inequalities, I highly recommend going into the book and maybe just using the snipping tool in your laptops, or you can just page it in the book or something to find that table of inequalities. Then our last caution here from the book, we have that equality and inequality symbols are used to write mathematical sentences. Operation symbols like plus, minus, multiply, and divide are used to write mathematical expressions that represent a number. So we're going to compare them. We see the sentence is that 4 is less than 10. It's giving us a relationship between 4 and 10. There's nothing we really need to do. We don't need to solve for a value. We don't need to do anything like that. It is just allowing us to use an expression. We're describing the relationship between two numbers. So we can think of it as more of an English skill. Whereas an expression would be 4 plus 10. And this is telling us how to operate on 4 and 10 to get 14. 4 plus 10 is telling us that we need to add 4 to 10 in order to get a specific value. We are not using it to describe the relationship, we are using it to solve. So a helpful clarification between using our inequalities and using our operations. All right, so that finishes up our lecture on section 1.1 for today. If there are any questions, of course, you can always stop by my office hours or anything like that. And I look forward to seeing you all in class tomorrow. So have a great rest of your day, everyone.